Hello, and welcome back to Introduction to Astronomy. Last class we talked about what to expect from this course, and also the basics of what's out there in space. Now, in this class, as we talk more about what's out there in space, we want to understand how we're figuring that out. How do we understand all this? How could we possibly know the qualities of some distant star or galaxy, aside from just taking a picture of it? And what if the picture is just a dot that we can't resolve? And the answer is, the tool we're using is light, and there is a lot of information in light. So a great deal of this course is going to be about how we use light to figure things out. So today we're taking a closer look at light, and this is going to continue into the next class as well, as our main tool for astronomy. All right, really, it's one of the only tools, assuming we cannot get in a spaceship and fly out to the moon and take some samples or whatever, because we haven't gone very far, right? The farthest we've ever gone is the moon. So assuming we don't have actual physical samples, if we want to learn about things that are very distant, one of the only ways that we can do it is light. There's really nothing else. You don't get sound in space. You can't listen to anything happening in there. And then what else is there? One example, one of the only other things I can think of is gravitational waves. And we've got, I think, maybe 20 observations, period, of gravitational waves. So really, it's light, all right? Light. That's what we do, is we take in light, and we need to get as much detail as we can out of that light, because it is the key to understanding everything that we can understand. So first off, light is a wave, and waves contain a lot of information, which is very useful. So a wave, a water wave, for example, if you throw a pebble in a pond, you get waves spreading out from there. There's high points called peaks, and troughs are the low points. If you have a leaf, for example, sitting on the water, then you can watch as the waves go. The leaf goes up and down. It is not actually being carried towards the person. It is going up and down. The wave is traveling. The material itself does not necessarily travel. So the leaf moves up and down, not sideways. All right, the wave moves, the material doesn't necessarily. So for example, sound travels in air. If you're in a room with someone and they speak, it's not like air is going out of their mouth and flying around the room until it enters your ear. That's not what happens. What happens is they shake the air with their vocal cords and stuff, and then the shaking of the air spreads all throughout the room until it eventually shakes the air inside your ear, and you pick that up, right? So the idea is a wave is a pattern of motion. It's a shaking of a material potentially, and it carries energy without necessarily carrying stuff. All right, it just carries energy from place to place. It does carry a lot of energy. All right, waves can cause damage, for example, but it's not necessarily carrying a lot of material. So here we see a wave on the ceiling, and nothing is moving, really. It's just lights turning on, and yet we see a traveling wave. But nothing is moving, right? But it is carrying energy. So waves, as we've already said, they have peaks or crests, and they have a low point called trough. The distance between two peaks or two troughs is called the wavelength, and it is literally a distance. So it's a length of the wave. It's not the length of the whole wave. A wave could potentially be the length of the entire ocean, but it's the distance between two peaks, all right? So it's setting sort of the scale of the wave. The frequency is the timing. So if you're at the Rogers Center doing the wave, how often do you get up and down? That's the timing. The size of the wave is enormous, but for your part, mostly what you pick up is the timing, all right? So we measure that with frequency, which is actually the number of up and down bobs, the number of waves that are hitting you per second. And normally with water waves, or in particular the wave at the Rogers Center, you're getting hit much less than once per second, right? You're not getting hit multiple times per second. But with sound, on the other hand, right? Sound is many times per second, and light is definitely many times per second that it'll strike a surface. Frequency and wavelength are normally related, all right? So these are not totally random things. If you have a big wavelength, you probably have a low frequency. If you have a high frequency, on the other hand, something is hitting you right, fast, if you have a high frequency, then you're going to have a short clustered wavelength. So you can imagine if you're sitting over here on the beach and these two types of waves are hitting you, this one down here with the longer wavelength, you get one splash, and then a while later you get another splash. So that's low frequency. It's literally not very frequent. On the other hand, if you're sitting over here at the beach and this wave is hitting you with a very short wavelength, then you're getting high frequency splashing, right? So there is an inverse relationship there. The bigger one is, the smaller the other is. And this is especially true of light. So we've got wavelength, we've got frequency, and the other main quantity that matters is the speed. How fast is the wave actually traveling, right? When you watch the water waves, how fast are they moving through the water? How fast does a sound wave travel? And obviously how fast does a light wave travel is pretty important, all right? So it's the wave actually traveling, remember, that carries energy. We can send sound. Sound takes energy to make, right? For example, I can speak from experience. It's tiring to talk for an hour. You put energy out and it is received elsewhere. And this is, by the way, I don't mean, you know, spiritual energy. I don't mean the energy of the room. I mean real. This is a measurable quantity, all right? Has to do with the size of the wave, the speed of the wave. Energy is a measurable quantity in science, and it is very important. But speed is what we want to focus on, I think, more. Speed depends on two things. It depends on, if you think about it, the bigger the wave is, right, that influences the speed. The size and the timing of the wave influence the speed. How big is it and how many times is it hitting you will pretty much tell you the speed. So for any wave, this is a key wave equation in physics. The speed is just the frequency times the wavelength. That's it. So now we are starting to get into our math, yes. And this equation, you know, a 3-term equation, is not too bad. But don't worry, if you haven't done a lot of math in a while, you do have to do it. But it will take some practice. And if you're not super comfortable, remember that you can always get comfortable with something, even when you haven't done it a long time or it seems very foreign, okay? So anyways, the speed of the wave is frequency times wavelength. Normally, we're going to write frequency as little f, italicized f. Wavelength is the Greek letter lambda. That's a lambda. And speed is normally given for a wave as c, especially for light. Light is normally given speed as little c. Why? Because. And so the equation that we'll normally write, and we're going to be seeing this equation a lot, okay? It matters. This is foundational for waves and light, is the speed of light in particular is frequency times wavelength. So how are we going to use this wave equation? So these quantities, these are real quantities, they have units. They are measured in something. I can't tell you that something is 10 away from me. Is it 10 meters? Is it 10 apples? Is it 10 people away? What is it? So we need units. Frequency, the frequency of something is measured in hertz or cycles per second. That's what hertz is. It's a short form for cycles per second. Well, hertz is named after the guy who, you know, came up with this stuff. But cycles per second. How many, or waves per second? How many waves per second are hitting you? All right. Again, with a water wave, it would probably be less than 1 wave per second. Seems weird to say that it might have a frequency of like 0.1 waves per second, a tenth of a wave per second, but I don't know, maybe. Anyway, it's going to be less than 1 for a water wave, right? But not necessarily for light. Wavelength is, as we already said, it's a length, so we're normally going to measure it in meters, and that is the standard. Okay, so we do need to use meters, not centimeters, definitely not inches. Meters is the standard. When you multiply them together, right, speed is frequency times wavelength. Cycles per second times meters, so that's meters times waves per second. That's meters per second. Right? It's actually meters per wave and waves per second. So when you multiply them, the wave kind of cancels out. If you want a little bit more detail on that, if you don't care. But meters per second is the measure of speed in normal physics. You could talk about kilometers per hour, you could talk about miles per hour, but meters per second is the standard. So we can do a quick calculation. And for the record, while you're doing these videos, please do, or watching these videos, please do have a calculator with you. so that you can try it, all right? Because the last thing you want is to be trying it on the test. You want to try it right now and get comfortable with it, all right? So let's calculate the speed of a wave that has a frequency of 3.5 times 10 to the 14 hertz. Oh boy, that is a, what, 10 to the 14? That's 100 trillion. 3.5 100 trillion hertz. That's the sort of frequency you get with light. Huge. There's a reason last class that we talked about needing big numbers and small numbers too, because light has a wavelength of 857 nanometers. Nanometers, and yes, you do need to know nanometers, is 10 to the negative 9. It's a billionth of a meter, right? That's nanometers. And that is the wavelength size for visible light. So I'm going to be saying nanometers a lot. So it does matter. So can you try that on your calculator? Give it a quick shot. And remember that I said this is something to be comfortable with, is on your calculator, if you have a scientific calculator, which you should, you can type in 3.5, and then there's a little button EXP. Can you find that button on your calculator? Push EXP and then just 14. And if you just push equal on that, and it'll show you that what you've just typed in is 3.5 trillion, all right? You don't have to do any extra work. You should not be typing in 3.5 times 10 to the power of 14. You will screw that up and it will waste time. Okay, you need to know how to do scientific notation on your calculator. So anyway, you've typed in the frequency, now multiply by 857 exp negative 9. Find the negative as well. It's not just a minus. There's a key to turn things negative. And what do we get? What we get is 3 times 10 to the 8. That's probably not exactly what your calculator is showing, but round it a little bit, and you get 3 times 10 to the 8 meters per second. And that is, lo and behold, the speed of light. So we can use this equation to solve for anything in the equation. Speed of light we don't normally need to calculate. It turns out that is a constant of the universe. We know it. It is given. We solved for that, a couple hundred years ago. We don't need to keep doing it. So we know the speed of light. Very often we'll need the frequency, or we'll need the wavelength. Or if you really are doing, if you're calculating this for speed of sound can actually change a little bit. So maybe you are calculating speed, Anyway, you can solve for all three of them. Here's the normal equation, C equals F lambda. If you want to solve for F, then bring lambda down, divide both sides by lambda. Cancels it out over here and brings it under the C effectively. If you want to solve for lambda, divide both sides by F. Lambda equals C divided by F. Do you remember doing this sort of algebra? A short form for this is this little triangle. Hopefully you do remember this, by the way. If you don't, it might be worth a little review of that, okay, because we will be using it. A short form for this is this little triangle over here that you can use, that whichever one you want to solve for, just cover up. So C equals F times lambda, F lambda. On the other hand, F equals C divided by lambda. And lastly, cover up the lambda, lambda equals C divided by F. But realistically, I think you should be more comfortable with the algebra than with doing this, because this equation, this triangle is very nice for this one sort of equation, but we are going to be playing with other equations in this course, and being able to handle a little bit of algebra, like moving something down under the other side, will be important. What is light? What is light? It has these useful quantities, and we will be talking about those numbers. What is light? Light is radiation. Radiation is often used as a word to mean something dangerous, right? Like, oh, if you watch Chernobyl on HBO, so radiation is normally implied to be dangerous, but really the word radiation just means anything that radiates. My voice radiates. Light is a special type of radiation. It radiates. Visible light is radiation. Now I'm an astronomer, or have an astronomy background. I don't do research anymore. I never actually said in the first lesson, did I? My research background is in planet formation. All right, this is a total aside, but since I never said, my research background is in planet formation, and a little bit of, I studied some galaxies and stuff like that. But anyway, nonetheless, with an astrophysics background, when I say the word radiation, I'm not thinking deadly radiation, I'm just thinking light. I'm thinking a wave, something that radiates. So, of course, we can't see it. Water waves we can see, they're obviously waves, right? Light, we are busy seeing. We can't really see its structure. In particular, the wavelength of light is extremely tiny, in the nanometers, right? But there is a broad range there. Nanometers is for visible light, hundreds of nanometers. There is a broad range of frequency and wavelength sizes for light that goes beyond what we call visible light. So again, when I say light, I don't necessarily mean visible light. I mean any part of the electromagnetic spectrum. Radio is light. Gamma rays are light. All of it is light. It is all electromagnetic radiation, all on the same spectrum. All right, so I will use these terms interchangeably because they are the same thing. So there is a broad range. Look at the frequency range down here, right? Look at the wavelength range. Radio is the biggest wavelength, as you can see in the picture. Radio is the biggest wavelength and therefore the smallest frequency. Radio can be kilometers in size. Microwaves are in the centimeters, and yes, those are the same things your microwave uses. Infrared is in 1,000th of a centimeter. Visible light in the 100th nanometer range. UV is even smaller, X-rays are even smaller, and gamma rays are down to 1/1,000,000th of a meter. But they have incredibly high frequency. So we start off with big to small or low frequency to high frequency. All right, like we said before, these are inverse quantities. The bigger the wavelength, like for radio, the smaller the frequency. And all these are on the same spectrum. They are all the same exact thing. They are an electromagnetic wave. We are only sensitive to visible light. That's why we call it visible light. We evolved around the sun. And you know what the sun mostly puts out? That range. The sun puts out most of its light right here. So that's what we evolved to see, and we call it visible light. But what if we evolved around a sun that mostly put out infrared? Then we probably would have evolved to see infrared, and guess what we would call it? Visible light. So visible is just the part we can see. There's nothing special about it, and in fact, it is an incredibly narrow region of the EM spectrum. Beyond that, there is so much more that's useful. Radio, microwaves, infrared. Then we get to visible, then we get the UV, X-ray, and gamma ray. And these are all very, very useful. We use them all on Earth, right? Radio we use a lot, microwaves you know, infrared is used for like TV remotes. UV is important because a lot of it can damage your skin, or maybe you just want to damage your skin like this lady. We got X-rays, you know. Gamma rays come mostly from radioactive things. They are dangerous. So we don't play with them a lot, but they do exist. So that's our electromagnetic spectrum, all right? Radio can be the size of buildings. Microwaves are the size of bugs. Infrared are the size of a ball in a ballpoint pen or a pinpoint. Visible light's the size of a bacteria, and then we get down to the size of molecules. X-rays are the size of atoms. Gamma rays the size of a nucleus. Tiny, tiny stuff down there, right? But it is all the same thing. It is an electromagnetic wave. A wave of electric fields and magnetic fields oscillating itself. And what makes it especially valuable is it oscillates through a vacuum. It can travel through nothing at all. Water waves need water. Sound needs air. But light can travel through nothing at all. And so astronomy can be done because the light will come to us through the vacuum of space. So visible light, the part that you're familiar with, of course, you know, visible light breaks down in a rainbow, right? Oh, surprise, surprise, it's the rainbow of light. Normal white light contains all that, right? White light, when it shines through a prism or through, for example, moisture, can be separated into the different colors. So red picks up after infrared, and we go red, orange, yellow, green, blue, indigo, violet, and then ultraviolet. Roy G. Biv might be familiar to you, right? Red, orange, yellow, green, blue, indigo, violet. But then we go to UV, ultraviolet. And with infrared and UV, they're not that different from visible light at all. The only difference is our eye can't pick them up, right? And of course, these are the same as the colors of a rainbow. That is what we're seeing. So normal white light coming from the sun, this is worth thinking about for a moment. White light contains all that. Simple white light contains all that and more. So now we're starting to think about, hey, is there more to light than meets the eye? Sorry for the pun, but Transformers. Anyway, so visible light, what we see as color, corresponds to different wavelengths. All right, that's all it is your eye will pick up different wavelengths and translate that in your head to different colors. So red has a certain wavelength, blue has a different wavelength. All right. So from violet to red, that's from 400 nanometers to 700 nanometers. And your eye is sensitive to different wavelengths in different ranges to different quantities, but in that sort of range. All right, so red is 700 nanometers. That is the bigger wavelength because it's closer to infrared and then radio, which is the biggest. 400 nanometers for violet is getting to the edge of what your eye can see, and that's the smaller wavelength. Right after that comes UV, X-ray, and gamma, which is definitely the very small wavelength. So often we'll talk about sort of the redder part of the spectrum, higher wavelength, and violet or bluer is the shorter wavelength part of the spectrum. All right, that's all color is different wavelengths. Now, we mostly do our astronomy from the ground, and it turns out we have an issue there, which is that not all electromagnetic radiation from space can actually make it to the ground. Radio passes through our atmosphere no problem, which is great. That's the reason why we can use radios, right? Because radios will pick up that radiation and turn that into a sound for you, and that wouldn't work if radio waves couldn't travel through the air. Infrared radiation can do an okay job of getting through the sky, but not great, and that the fact that it partially blocks radiation is part of the reason for climate change. Well, it's the main reason for climate change. Visible light goes through the air no problem, which is why, again, you can see through the air, and we can see into space, thank goodness. We can see the stars. UV is largely blocked by the atmosphere, the ozone layer, but obviously, as you know, if you've ever gotten a sunburn, plenty of UV gets through. The reason why it burns your skin, by the way, is because it is the higher energy range, and it can actually do damage to your skin cells. Then we go to X-rays and gamma rays, and those are actually completely blocked. Our atmosphere is opaque to X-rays and gamma rays. It doesn't let any of them through, and thank goodness for that. When we get out into space in a spaceship or something, right, the few lucky astronauts who have ever been able to do that, and certainly if we ever wanted to set up a colony on Mars, which has a thin atmosphere, we would have to worry about, without Earth's atmosphere to protect us, how much X-ray, gamma ray, and UV are we being exposed to. So it turns out all these types of light travel at the same speed. All right, it's called the speed of, well, it's called the speed of light, isn't it? So yeah, it's called the speed of light for a reason. It's not called the speed of X-rays and the speed of microwaves. It's called the speed of light, and the speed of light is 300,000 kilometers per second. All right, 300,000 kilometers per second, or 300 million meters per second, or 3 times 10 to the 8, right? 3, 6, 7, 8. 3 times 10 to the 8 meters per second. And they all travel at this speed. You might say, oh, but isn't gamma ray like faster? It has a higher frequency. That doesn't mean, so that means it would impact your skin more frequently. That doesn't mean it's traveling faster, because don't forget, the reason why it's impacting your skin so much more frequently is because it has such a teeny wavelength. So one arrives and then the next and then the next and then the next. But it travels at the exact same speed as radio. Radio is just so spread out that it has a lower frequency of contact with you. One arrives and then another arrives and then another arrives. But they are nonetheless traveling through space at the same speed, 3 times 10 to the 8 meters per second. All right, so that's a key number for us. Speed of light is key, and in fact, we spent a great deal of last class talking about that already. So the other thing that I've already mentioned a couple times is the energy. Gamma rays are high frequency and high energy. Frequency is related directly to energy. The higher the frequency, the more energy, and the more danger. So gamma rays are higher energy and higher frequency and short wavelength. Same speed as radio. Radio has a longer wavelength, lower frequency, lower energy. Radio is very low energy. It is cheap to make, which is one reason why we use it a lot. It is literally cheap. It is low energy. Gamma rays are high enough energy, on the other hand, and X-rays are high enough energy too, for the matter. They can blow right through you. The real danger is if they hit a molecule on the way, in particular, if they hit DNA on their way blowing through your body, they can actually shatter the DNA molecule and kill a cell. And UV can do this too, although it can't penetrate as deeply because it's not as high energy. So UV is a threat to your skin cells. X-ray and gamma ray can penetrate right through you and do damage throughout your body. So they really are high energy and high danger. So what we're going to look at next now is temperature. When we get light from something, we can use that to gauge its temperature. And to some extent, you already know this. This is going to be, to some extent, familiar to you and obvious maybe. But this is key because it's going to tell us when we look at a distant star, we can actually easily figure out its temperature. So as you well know, if you take something and make it hot, then it can start to glow. So here we see heating up a piece of metal, and as it gets hotter, it starts to glow more and changes color. And those two facts, the fact that as it gets hotter it glows more, and the fact that its color changes, are the two keys that are going to help us understand temperature. So the color of the metal depends in particular on the temperature. If we think about heating something up more and more, as an object is heated, it puts out light at all sorts of different wavelengths, right? Many different colors, and it will change color depending on the temperature. So it will start off at red, which is going to be low temperature for something that is actually glowing, orange, yellow, and then it'll go all the way to white. At white, the truth is it's going to be emitting red the whole time. But once it starts adding in yellow and orange, and then it starts adding in blue, the eye is not going to be hugely sensitive to that, and so the eye will mostly see it as just white. And in fact, if you look at the sun, which, you know, don't do that a lot or for long, but it's white light because it's putting out everything. And obviously the sun is pretty hot. So yeah, here's sort of an obvious question for you. Here we're using a blue torch to essentially weld something. Why can you not do that with a candle? A candle is just not putting out anywhere near as much heat. And it is as well a very obviously different color. The color of flame can be quite indicative of the temperature. Again, as you should know, right? What is the hottest color of flame? Hopefully you know, right? So when you heat anything, it's going to put out light, and everything has some heat, right? There's nothing at 0 degrees. So everything is going to emit some amount of radiation, and how much and what kind of radiation emits depends on the temperature. The hotter the thing, the shorter the wavelength of light that will be emitted, all right? The smaller the wavelength, but don't forget, small wavelength means high frequency and high energy. So the hotter the object, the shorter the wavelength, but the higher the frequency, the hotter the object, the more energetic the type of light it's putting out. Something that's not very hot may be putting out infrared. Something that's incredibly hot could be putting out visible light, UV, or more. You get up into the tens of millions of degrees, and a super hot object can actually emit X-ray, very high energy, but a very short wavelength as well. So we have some temperature, right? Do we emit light? Of course. But if you turn off the lights in a room, we don't glow in the dark, right? We are not emitting visible light because we're not that hot unless you set someone on fire, which please don't for the purposes of this course, or any purposes at all, actually. Don't set people on fire. But anyway, the point is, we don't normally emit that much light because we're not that hot, but we are not 0 degrees. We are warm, and we do emit some type of light. We do emit infrared. So we're not energetic enough, we're not hot enough to put out that small a type of light as visible. Our type of light is a little bit bigger wavelength because we're not that hot, and that's infrared. So as you may know, if you have an infrared camera, for example, right, you can see people glow in infrared because we're the right temperature for that. And a lot of things in astronomy actually are not hot enough to glow with visible light. For example, a planet, right? Earth or the moon or any of the planets in the solar system are not hot enough to glow with visible light, but they do reflect sunlight, which is how we normally see them. But if you use an infrared camera, then you'll actually pick up the light the planet itself is producing because they are warm enough to put out infrared. So if you want true information about something like a planet in space, you can use an infrared telescope. And we do have infrared telescopes for precisely that reason. In space, we need all the information we can possibly get. And so we don't restrict ourselves to visible light. We have radio telescopes, microwave telescopes, infrared telescopes, gamma ray telescopes, everything. Now, here we see a graph of the amount of light something is producing in scaled units. So not too important what unit that is, but the amount of light versus wavelength. Nothing is going to be putting out the same amount of light at all wavelengths, right? I just told you that we put out light mostly in the infrared, 0 in the radio, 0 in the microwave, basically 0 in visible, 0 in X-ray. So if you do a graph of how much light we're putting out versus wavelength, you'll see that we're mostly peaking in the infrared. So here's some real data for the amount of light something is putting out versus the wavelength of a given star. Okay, so this is effectively real data. How much light is something putting out versus wavelength? And what we can see is indeed there is a peak. About 500 nanometers is where it peaks. It's putting out very little in less than 200 nanometers. Then it starts to go up. It's putting out more and more and more light. At 500 nanometers, that's the wavelength. It is putting out the most light. It's still putting out light at 600, 700, 800 nanometers, but less and less and less and less. Right? And as we get to bigger wavelength, we are going to smaller frequency and smaller energy. We are going towards, this could be visible light. Well, it is visible light, 500 nanometers. And then we're going from there to bigger wavelength is getting towards infrared and radio, and a star will put out less and less and less and less. Right? Most stars are going to peak somewhere near the visible spectrum. That peak, the shape of that, is very standard. And it's got a classical name, a name sort of derived from when this was, from historical purposes, it's called black body radiation. All right? So any hot object, a theoretical, idealized hot object that absorbs everything that's hitting it, gains temperature, and emits everything perfectly. This is a hypothetical object because nothing is quite that perfect. But a hypothetical object like that is called a black body. Black because it's absorbing everything, coming to a standardized or equilibrium temperature, and then emitting based on that temperature. That would be a black body, putting a black body radiation, which has that standard curve. And stars are actually pretty good as black body radiation objects. They're not black, they're putting out quite a lot of visible light, but they pretty much absorb everything that hits them, and they put out radiation based on their temperature, more or less. So they are decently good examples of just a ball, a black body emitter. So black body radiation has a certain spectrum. And spectrum, if you think about what a spectrum is, you're used to the spectrum as being the different colors, right? But those are different wavelengths. So a spectrum is best done as a graph of how much light is something putting out at different wavelengths, which is the graph I already showed you. Here we see wavelengths of whatever unit, it doesn't really matter, but this exact shape, right? This shape is what you get from a black body emitter. The intensity, the radiation, the amount of radiation, the intensity rises, comes to a peak, and then more slowly falls off. And that is the precise curve that we would expect from basically any black body emitter it'll just peak higher or lower, and to the left and to the right, but they all have this exact shape. So if you measure the spectrum for a glowing iron bar, for example, or a star, or the temperature of the universe, you get pretty much the exact same shape. That's a black body radiation curve. So here's some examples of black body radiation curves, the spectrum that you get from 3 different stars at 8,000 degrees, 10,000 degrees, and 12,000 degrees. And you see 3 different curves. They are all the same shape, just peaking at different wavelengths and at different heights. Obviously, the bottom one doesn't look quite the same, but if you stretched it back up to the same height, then it would look identical. All right, so they are all the same shape. There is a mathematical equation for that shape. It's a complicated equation. I'm not going to show it to you, but it depends really just on the temperature. All right, so these all have the exact same mathematical shape depending on the temperature, and the temperature does differ: 8,000, 10,000, 12,000. So these are all 2,000 degrees separated. All right, and so here you can see 3 different objects, 3 different stars on the same spectrum graph, and you can see the differences. The peak is moving to the left, smaller wavelength, as you get to higher temperature, which is what we already said. Hotter objects will have smaller peak wavelengths. All right, the peak rises and moves to the left. So those are the 2 keys for a black body curve. Here we see 3 different black body curves, very similar, right? Not so hot, very hot, really hot, intensity versus wavelength. And this is the visible part of the spectrum right here: red, orange, yellow, green, blue, indigo, violet, right? This is the only part that we can see. So when I ask you what it would look like, you got to consider what is the part that we're seeing. The rest we don't get to see, but it's still there, right? So the first thing to notice is that the peak wavelength, right? What wavelength is it peaking at? This one looks like it's peaking at maybe 200 nanometers. This one is peaking at about 500 nanometers. This one's peaking at about 1,000 nanometers. The peak wavelength is the wavelength at which the most radiation is given off, right? The hotter the object, the peak shifts to the left, shorter wavelength or higher frequency and higher energy. The really hot object is putting out most of its light in UV. The not so hot object is putting out most of its light in infrared. And the simply hot object in the middle is putting out most of its light in the visible. All right, the hotter you get, the more you shift to lower wavelength, higher energy, and higher frequency. Which shouldn't be surprising, right? Of course, something that's hotter is going to be putting out more X-ray than you, right? So here's another graph of the exact same thing. The wavelength, and we can measure this, right? We can measure exactly where does it peak. The wavelength here is 505.7 nanometers. That's the peak wavelength. That's an important one. Lambda max, right? The maximum peak wavelength. And where this peak occurs is the most important part of the graph. We can measure this for a star. We can take a spectrum of a star. Most telescopes don't take a picture, all right? We're a little bit beyond that now with our level of technology. We can do better than just take a picture. What we do is we take a spectrum. Most telescopes will take a spectrum, and you'll get effectively a graph that looks exactly like this. And if you can figure out where the peak wavelength is, which you can by just looking at it, there it is, right there, right? Done. Then you can relate that to the temperature. The peak wavelength can tell us how hot the object is. And that's the big key for today, right? The peak wavelength, 505.7 nanometers, that tells us exactly how hot this thing is mathematically, all right? So the 2 things to notice, right? The hotter the object is, the more light it gives off at all wavelengths, actually. So this graph is slightly different. This graph is a logarithmic graph. Instead of just going 1, 2, 3, 4, it's going 10, 100, 1,000, 10,000, 100,000, a million nanometers. So it's a logarithmic graph. It's going by powers of 10 on the y-axis and the x-axis. And so they look more like just bumps, right? Instead of coming up slowly and then sort of tapering off, they look like big bumps. Notice The hotter the object, so a sun compared to the light bulb, compared to the stove, compared to a rock, the hotter object puts out more light at every wavelength. So notice at a million nanometers, the sun puts out more energy, puts out more light, higher intensity than a light bulb, which is putting out more than the stove, which is putting out more than a rock. That shouldn't be surprising. At 10,000 nanometers, the sun is putting out more than a light bulb, which is putting out more than the stove, which is putting out more than the rock. At all wavelengths, the hotter black body will give off more light than a cooler one. All right, that should not be surprising. Okay, so at all wavelengths, no matter what, a hotter object puts out more energy. All right, and then the peak tells us directly the temperature. Where it peaks is going to tell us the temperature. So a 20 degrees Celsius rock peaks somewhere at 10,000 nanometers. The sun peaks a lot closer to, actually it peaks around green. So it peaks in the visible part of the spectrum, whereas the rock peaks in the infrared, right? So the peak of the black body curve in a spectrum moves to shorter wavelengths for hotter objects. All right, those are the two key facts. Hotter thing puts out more light at all wavelengths, and it peaks at a shorter wavelength. So none of this should be surprising. A hotter object puts out more light, no surprise. A hotter object, as you heat something, it goes from red to orange to yellow to white and even blue, right? Hotter objects have shorter wavelengths. To be honest, this is mostly common sense. I know that as kids, you often draw, you know, I mean, I've got two kids, right? So I watch them draw and color things, and they say a cold thing is going to be blue because ice is like blue, right? Red means hot, right? But we know that's not really true. If you've ever, you know, depending on if you're a pyromaniac or not, you would know a hotter flame burns blue, right? So blue is hot, hottest. Only the hottest flames are blue, right? Whereas red is cool. And I know, you know, as an artist, you would often say blue is for ice, red is for fire, but that's not what we're talking about here. We're talking about taking an iron bar and heating it. And so it'll go from red to orange to yellow to green, all the way to blue if you could get it there. All right. So a blue star, for example, and yes, stars are blue if they are ultra hot. Our sun peaks more in the middle of the visible light spectrum. It actually peaks somewhere near green. But to our eyes are not super sensitive to that, so our eyes see it as more yellowy or just white. Cooler stars are red, the hottest stars are blue. All right. The hotter the object, the more it peaks to the shorter wavelength, to the blue, even to UV. All right. So there are stars that are 18,000 degrees or more, and those stars are blue, whereas the cool stars are more red. All right. And again, you should know this, which stove is hotter, right? Which stove is hotter? I'm not asking you to put your hand on it either way, but which stove is hotter? The blue one. The blue flame burns hottest, right? You know that. You better know that. If you didn't, now you do. And you're welcome. I just saved you from third-degree burns. Moving on. So if we look at stars, if we look at actual stars, you can see this, okay? Again, the human eye is not ultra sensitive to these slight differences because all stars are putting out all these types of light. The eye is not super sensitive to the differences, but the hottest stars will appear distinctly blue, and the coolest stars will appear distinctly red, all right? Most will look just white, slightly yellow, because our eye is not super good at telling the difference. But in truth, there will be strongly blue stars and very red stars as well. So if we look at the Orion constellation, for example, which is the least hot star, which is the coolest star here? Betelgeuse, right? The coolest star here. That's actually a red supergiant. It's actually a huge star, but it's dying, so it's fairly cool on the surface. And we'll talk more about that. All right, so that's not too hot. So what I've been telling you again and again is that a hotter star will have a smaller peak wavelength. That has got a name. That is called Wien's law. all right? And it has an equation as well, and that the equation is Wien's law, all right? So peak wavelength is inversely related to temperature. The bigger the peak wavelength, the lower the temperature. The lower the temperature, the bigger the peak wavelength. Or the hotter the temperature, the higher the temperature, the lower the peak wavelength. Either way, they're inversely related. Okay, higher temperature is smaller wavelength. We've been saying this again and again and again. I do think that if I say higher temperature is smaller wavelength, lower temperature is bigger wavelength, it starts to become almost confusing. but it's not. It's the same thing we've been saying this whole time. Hotter thing, peaks in the blue, right? So peak wavelength is the only factor in determining the temperature of a star. That's it. That's it. So if I get the spectrum of a star, all I have to do to figure out the temperature of the star, I don't have to fly out there and stick a thermometer in the damn thing, because I can't, so that's good. All I have to do is find a peak, and I'm done. That's it, all right? And this is what astronomers do, all right? So let's check it out. Here we've got 3 stars. The graph I've already shown you a few times. Which of these 3 stars is the hottest? A, B, or C? A. It peaks to the left, and it's also got the highest peak, so that's a good hint. But don't pay too much attention to the height, because there is a trick with the height, all right? The size of the star will also impact the height, but the location of the peak, that will tell you the temperature, okay? So look more at where does it peak, and A peaks most to the left, to the lowest wavelengths, so A is the hottest. Which object is the coolest? Again, thinking about the peak, not the height. Where is the peak? Star C has a peak furthest to the right, furthest to the big wavelengths. So it is the coolest. Which would appear red? That's a good question. Which would appear red to our eyes? And consider our eyes are only seeing the visible part of the spectrum. So think about what it's putting out in the visible part of the spectrum. Which star would appear red? Star C. Look at star C. It's putting out more red than blue. They all put out all colors. They all put out all colors, but star C is putting out more red than blue. So what color is star C going to look? Red. What about star A? It's putting out way more blue than red, so what color is it going to look? Blue. And we already said the hotter stars are going to look blue. That's why. Because look at the slope of this line. It's going up. It's got more blue than it's got red. Now, but you might say to me, but Dave, star A is putting out so much more red light than star C. So yeah, question 4, which object gives off the most amount of red? A. A is putting out way more red than C. But so what? If you look at star A, that doesn't mean it's more red looking. It puts out, star A on its own, sitting there in space, puts out way more blue than it does red. So it will look blue. We already said that a hotter object puts out more light than a cooler object at all wavelengths. So of course star A is putting out more red than star C. But star A is putting out more blue from its surface than red from its surface, and so it will look blue. All right? Which object gives off the most amount of blue light? And of course, just look in the blue. A is putting out way more blue than anything else, which again, we already know. A is the hottest object. It'll put out more blue. It'll put out more red. It'll put out more green. It'll put out more yellow. It'll put out more of everything than anything else. But if you look at A, it'll look blue. If you look at C, it's putting out more red than it is blue. It'll look red. B will look to our eyes maybe a bit blue, probably blue, I guess. B will look mostly blue, but more white than anything else. Okay, so now let's talk about actual numbers. How do we measure temperature? I think you know, with a thermometer. And when you use a thermometer, it's probably giving you Celsius. Fahrenheit is not allowed in this course because Fahrenheit is stupid. But Celsius is good enough. 100 is boiling water, freezing water is 0. But there are negative numbers in Celsius, and we don't really want that. If we're going to measure something, we want to measure from 0 up, right? So what we can do, because Celsius bottoms out at negative 273.16, that's stupid. Let's just bottom it out at 0. And we call that the Kelvin scale. Kelvin temperature goes from 0 up. And so shift everything by 273.16. So take all these numbers and add 273.16. Kelvin bottoms out at 0. Freezing water is 273.16. Boiling water is 373.16. All right. We call the bottoming out, we call that absolute 0. And the truth is, there is no such thing as absolute 0 in our universe due to quantum mechanics and other fun stuff. But that's essentially when something has no heat in it whatsoever, and the atoms would ideally come to a complete stop. They wouldn't even vibrate. They aren't moving. Nothing's moving. Everything's completely stopped at absolute 0. And the truth is that doesn't really exist, but that's the idea anyway. So Kelvin goes up from 0. And that makes it a very useful thing. And it's just shifted off Celsius by 273.16, right? So let's do some practice, all right? And then we're going to get to some math as well. Star A and star C. Which has the longer peak wavelength? And this is a different picture than I showed you before. Which has the longer peak wavelength? Star A, star C, or are they the same? I'm not asking for which one is taller. I'm asking for the peak wavelength. And look at that peak wavelength. It's the same. They have the same peak wavelength. So what does that tell you about their temperature, right? Which star has the lower surface temperature? Which star is cooler? Star A, star C, or are they the same? And if they have the same peak wavelength, what does that tell you? Could you hear that? My daughter was trying to get in the door. she just then goes stomping away. Anyway, my wife is taking care of her right now, not me. I'm not neglecting my children, I swear. Which star has the lower surface temperature? Star A, star C. Well, they have the same peak wavelength, don't they? So it's got to be the same. They have the same temperature. So take a guess. If they're the same temperature, why is it that star A is putting out more light than star C? It's bigger. They are the same temperature, but star A is bigger. So like we already said, peak wavelength depends only, temperature depends only on peak wavelength. So don't trick yourself here. They have the same temperature. Star A is just bigger. All right. So star A is bigger than C, but they have the same peak, so they are at the same temperature. Which of these two stars looks red? A, C, both, or neither? Look in the visible part of the spectrum. Both of them are putting out more blue. And again, the eye is not very sensitive to violet and indigo, so we tend to call the left side blue and we call the right side red. Okay, so both of them are putting out more blue than red. So which of them looks red? Neither. They're both blue stars. Okay, now we've got a complicated graph. Ooh, look at it. These are 3 different stars at 3 different temperatures, 3 different sizes. Which of these stars is the highest temperature? Which peaks to the smallest wavelength? And that's going to be star A peaks to the smallest wavelength. All right. It gets complicated if I ask you, which is the biggest? Let me put it this way. Star C is super cold compared to star A, right? So why is star C almost at the same intensity peak? It's almost putting out as much energy. It must be really big. Star B is obviously also really big. So between the two of these, I don't know which one is bigger, but they're both obviously bigger than star A. That's the only way they can compete. because they are cooler, and yet they're putting out a lot of light. So Wien's law, let's make it math, all right? Wien came up with the exact relation between peak wavelength and temperature, all right? The temperature is going to be 0.0029 divided by the peak wavelength, or you can swap those, all right? Bring lambda peak up and bring temperature down. Either way, the equation has the exact same form. The peak wavelength is going to be 0.0029 divided by the temperature, assuming you're doing wavelength in meters and temperature in Kelvin, all right? So wavelength must be in meters. So if I gave you something like 580 nanometers, you would have to put in your calculator 580 exp -9. Okay, you would have to put in 5 times 10 to the -9, or 580 whatever, divided times 10 to the -9. Okay, so you got to be putting it in meters, and temperature will be in Kelvin. All right, Kelvin, again, 0 to 373, where Celsius goes from -273 to 100. So we know what Kelvin is. Okay, so we can do it. We know everything we need to. Wien's law is actually very simple. Normally, what we're going to do if you were an astronomer is you would get the peak wavelength and you would figure out the temperature. That's how we know the temperature of these different stars. All right, so we can calculate the temperature of anything in space just by using its peak wavelength. So if we measure the peak wavelength, 600 nanometers, whatever, we can figure out the temperature of that thing without having to fly out there and sticking a thermometer in a star. Okay, or on the other hand, if for some reason you knew the peak wavelength, you could calculate the temperature. So for example, I know I could stick a thermometer in a person, or maybe ask them to put it under their tongue, and I could get their temperature or their skin temperature, and then I could figure out what peak wavelength they're at, and it would be in the infrared. Okay, so let's do it. What is the temperature of a star whose peak wavelength is 380 nanometers? Give it a try. All right, and don't forget, in your calculator, you got to put in 380 exp -9. So 0.0029 divided by 380 times 10 to the -9 meters. Please calculate that for yourself. Try it. Make sure you can do it. Okay, feel free to pause this video and take as long as you want. Here's the answer. It is 7,631 Kelvin. If you're curious, subtract 273 and you get 7,358 Celsius. And that's how hot the object is on its surface. I do not have to fly out and stick a thermometer in a star. I just measure the peak wavelength. And that is easy to do with modern astronomical equipment. It'll pretty much give it to you automatically. So that's one way we study stars, is we do exactly this. So let's try the opposite, because it's basically the same calculation. Let's say I know somehow that a star peaks, that a star has a temperature of 11,500 Kelvin. What would be its peak wavelength? And it's going to be the same sort of calculation, but now I'm solving for lambda peak. Lambda peak is going to be 0.0029 divided by 11,500. That's a little bit even easier to do on your calculator. Have you got it? It is 2.52 times 10 to the -7 meters. How do you put that in nanometers? What you got, this is 10 to the -7. If you want this in nanometers, you got to actually shift the decimal place back 2 more to get to -9. When we do negative, we shift the decimal back, right? So you got to shift it. It's going to be 252 times 10 to the -9 meters, or 252 nanometers. And that's it. That's it for today. So next class, we're going to be continuing a little bit more with light and how we can do very interesting things with light. We can learn about the composition of things with light. We can learn about the motion of things with light. Everything we can know about the universe, we got to get out of light. So next class, we're going to look a little bit more at that. That'll take us to an early observation of the motion of galaxies which told us the universe is expanding, which told us the universe had a birth in the Big Bang. Very, very big ideas, very, very important stuff. So that's going to be next lesson. But for now, what we're going to do is we are now going to do our lesson together. So you can head over, we're going to work on our homework together and dissect more about the color, temperature, wavelength, speed of light, all this fun stuff, and some more calculations to do with light.